One of the remaining unsolved problems in our understanding of the universe and its formation is the baryon asymmetry. Namely, why is there far more matter than antimatter in the observable universe? Antimatter is the reflection in the cosmic mirror of matter. It annihilates with matter when they interact, producing pure energy. When experiments like LHC at CERN measure the production of antimatter in particle collisions, it turns out that the production is quasi-symmetric. The same number of particles and antiparticles is almost always produced. This symmetry has an implication for the theory of the Big Bang. In the beginning of the universe, as many particles as antiparticles must have been produced, but nowadays we detect almost no antiparticles at all in the whole universe. This is the so-called baryon asymmetry. In other words, if there was as much matter as antimatter, all of it should have annihilated shortly after the Big Bang. But we do have a baryonic universe that is mainly composed of matter. The solution to this puzzle could be a double agent, a particle capable of playing the role of matter or antimatter and introducing a tiny asymmetry in favour of matter. This double agent must fulfill two conditions. It must be an elementary particle, and it must be neutral because electric charge is inverted in the other side of the cosmic mirror, so a neutral double agent candidate could behave as both. The only particle that meets these requirements is the neutrino. It could mediate reactions leading to a slight excess of electrons and of quarks in the early universe. Thus, the balance would be tilted to the matter side and the universe would survive. How would we know whether the neutrino is its own antiparticle? We just need to detect a neutrinoless double beta decay, an extremely rare reaction where a stable atom emits 2 electrons and decays to a daughter cation with a double positive charge. Xenon-136 is one of the few isotopes that could undergo this reaction and the choice of the next experiment. It's an ideal candidate to use because its electroluminescence properties can be used to detect the electrons. As they travel through the xenon, the 2 electrons from the reaction ionize the medium, leaving a track in the process. The next experiment can already reconstruct this track. A version of the reaction with the additional emission of 2 antineutrinos is already known to happen, 2 neutrino double beta decay, and it takes 10 to the 21 years, while the age of the universe is only 10 to the 10 years. The version of the decay without neutrinos is expected to take even longer, at least 10 to the 27 years. And it must be distinguished between thousands of background reactions coming from natural radioactive decays. This is equivalent to looking for a particular grain of sand in a beach of 70 kilometers square. The latest objective of the next collaboration is to detect the daughter cation in the reaction, barium-136. A molecule tailored to capture this ion has been synthesized. The molecule has the property of emitting fluorescent blue light when it has captured barium and green when it hasn't. A monolayer of these molecules inside the next xenon chamber will capture the baryon ion and shine blue light. At the same time, the 2 electrons emitted will be detected, proving the occurrence of the neutrinoless double beta decay. How difficult is this? Next is trying to detect one barium atom among 10 to the 28 xenon atoms. Imagine all these atoms as fish in the sea and our molecule as a fishing net. The number of xenon atoms would correspond to the number of fish we would have in all the oceans of a planet, in all planets of a galaxy, in 100,000 galaxies. Imagine trying to catch one specific fish among all the others.